Alright, so we know how to take the derivative. We know how to take the derivative of natural log. So then that naturally leads us to the integral of 1 over x then has to be defined as the natural log of x. Now usually when you integrate 1 over x, you write it as the natural log of the absolute value of x. All that means is x cannot be negative. So it's just the way that we usually write the integral of 1 over x. Or whatever, if it's a natural log that you get, just put your answer in absolute value bars. Okay? If you think about the derivative of the natural log of u, remember that was 1 over u du. So basically, or that leads you to suspect that the integral of 1 over u du is the natural log of u. It's the natural log of absolute value of u plus c. So remember, the du has to be present in order to integrate. The du has to be present in order to integrate. So what does that mean? What does it mean? Alright, let's see. Let's say I had the integral of 4 over x dx. Okay? If you have noticed, when finding the derivatives of natural logs, what are we getting? Fractions. 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 So when you see a rational expression or a fraction or a quotient, the first thing that you want to think about is this a natural log integral? The way that you can tell, is this a natural log integral, is you look at the denominator and let the denominator be your u. If you can let the denominator be your u and you have the du present, or in this case, on this problem, the du is 1, or 1 dx. So there is no x that needs to be in the numerator. There's just, is there a constant in the numerator? Yes. There's nothing to bring out because it's a 1. So that means that the integral of 4 over x is equal to the natural log of the absolute value of u, which is the natural log of x. What did I have here, though? This constant needs to be written in front, which can then in turn be moved where? Up there. Up where? Up there. So it can be written as an exponent. Do you have to write it as an exponent? No, you do not. But it can be written as an exponent. Also, if this exponent that you write up here, if these absolute values drive you crazy, if you move an exponent up here and it's an even number, guess what? You can drop the absolute value bars. Why is that? Because if you have an even power, that ensures that whatever you plug in will be positive. After you take it to the 4th power, any even power, that makes whatever you're taking the natural log of positive. Now, does that mean you have to do this? No. You could just write your answer as 4 natural log of absolute value of x plus c. And I'd be fine with that. Alright, so let's say that I was walking down the street and we run into this integral here. 1 over 2x plus 1 dx. So I see the integral of a fraction. My first thought in my mind needs to be, hey, is this a natural log integral? It doesn't have to be just because it's a fraction, but it might be. And this is one of the very first times that you are able to integrate fractions, unless it's U-substitution. And I'll show you the difference. I'll show you what a U-substitution integral looks like, and I'll show you what we'll compare that to a natural log integral, just to see the difference. Alright, but if I was looking at this, then can I let the denominator be my u? So if let's say u equals 2x plus 1, what is du equal to? 2. So I don't have a variable in the numerator, that's good. So because I just had a constant here. So what do I need to bring out? A 1/2, right? Because if the du has a 2, you bring out a 1/2. So now I'm going to rewrite this integral for you so you can see what form it's in. If I say my u is 2x plus 1, and the only adjustment I have to make for my du is maybe bringing out the reciprocal, there's no variables and there's no variable here, then that's the form it's in, 1 over u du. And we know that the integral of 1 over u du is the natural log of u plus c. The only thing you have to do is don't leave your final answer like this. Alright, plug your u back in. So that's natural log of the absolute value of 2x plus 1 plus c. Now remember, the good thing about integrals is you could take the derivative of this and check your answer. You don't have to, but if you take the derivative of this, you will get 1 over 2x plus 1. Alright, so when you see a fraction, if it's not U-substitution, meaning you just don't see that it's a integral like we were doing in 4 or 5 or whatever section it was, one of the previous sections, then you need to say, is this natural log? Alright, is this natural log? And so the way that you can tell is, if I let the denominator be my u, do I have my du present? Okay, so look at this one. Alright, I see a fraction. The first thing I think to myself is this a natural log integral? So the way you can tell, take your denominator and let that be your u. Find your du. So du equals 2x. Now, the variable part, since I do have a variable part in my du, has to be up top here. This x has to be in the numerator, x to the first. If it's not, then something's wrong. It's not a 1 over u du integral. It is. What do I need to bring out? A 1/2 because of this 2. So I can rewrite this integral as 1/2 times the integral of 1 over u du. Okay? So that, if it's in the form 1 over u du, that is a natural log integral. So this is 1/2 times the natural log absolute value of u plus c, or 1/2 times the natural log of x squared plus 1 plus c. So that is a natural log integral. So now it's time for me just to flip your world upside down and try to confuse you. Not really, but I want to show you an integral that you should have been able to do coming into today that kind of looks like this one, but it's not a natural log integral. Most of you probably either saw me work one out like this or worked out several on the homework last class meeting. Now, look at this integral. That's the one we just did that we figured out as a natural log integral. And look at the one that I'm about to write up here. And what is the difference? The difference is, on this one, my denominator is being squared. All right? So if I see this and my first thought is this a natural log integral? For this to be a natural log integral, you have to say, well, can I let u equal x squared plus 1 squared, the entire denominator? So what would my du have to be for this to be a natural log integral? Well, the du here is 2 times x squared plus 1 times 2x. Is all of that, and that would be 4x times x squared plus 1, is that in the numerator? No. So this is not a natural log integral. Like I said, this is one that if I would have never shown you anything about natural logs and you understood U-substitution integrals completely, this is one that you could work out. You would have said, if you know nothing about natural logs, you would have looked at it and you would have said, okay, there's something in parentheses, regardless of where it is, there's something in parentheses being raised to a power. So you would say u equals x squared plus 1. So then du is equal to what? 2x. So look, this x is present up here. Now here's the key to working out the integral. Of course, we know we bring out a 1/2, but the key to working out this integral now is when we rewrite it, it's 1 over u squared. That is not natural log. 1 over u squared is not natural log. It's 1 over u squared. Okay? So you say, okay, that's 1/2 times the integral of u to the negative 1. Sorry, that was du, not dx. du. So, wait, negative 2. Why did I put negative 1? I was trying to integrate. I hadn't integrated yet. So how do I integrate this? Add 1 to the power. What does it become? U to the negative 1. And divide by what? Negative 1. So this is going to be negative u to the negative 1. I believe one like this possibly could have been on your last test. So that's 1 over 2, or negative 1 over 2 u to the first, or negative 1 over 2 times, what was my u? X squared plus 1 plus c. It's very important that when you see a quotient, you can recognize that it is in the form that you would need for the integral to be natural log. Okay? For example, I know I'm just doing more of the same, but you can never work too many of these. You may can work enough of these, but it'll never be too many. Oh, that needs to be squared, sorry. Alright, so the integral of 3x squared plus 1 over x cubed plus x dx. So when I see this, the first thing that I think, I'm not thinking U-substitution, even though it might be. The first thing I think is this a natural log integral? So I'll look at the denominator, and if in your mind you can just take this denominator and take the derivative, 3x squared plus 1. Is that what's in the numerator? Yes. So it's a natural log integral. After you work so many of these and you can just look at the denominator, you say the derivative's in the numerator, then you don't have to write down all your u and du and rewrite the integral, but it takes practice to be able to do that. So I mean, but if you see the denominator and you see that the derivative of that is in the numerator, then it's natural log absolute value x cubed plus x plus c. Yes, you have to be able to do a little mental math to do that, but that's fine if you can do it. Look at this one. The integral of secant squared x over tangent x dx. So you look at the denominator. The denominator is tangent x. What's the derivative of tangent x? Secant squared. This is 1 over u du. So what would this be? Again, I'll write that down. If you let the denominator be your u, your du is present. Exactly what we needed right there. So 1 over u du. That'll be the natural log absolute value tangent of x plus c. 1 over u du. 1 over u du. Okay. Now I want you to look at this one here and pay special attention to the du. Alright, so let's say I had the integral of x plus 1 over x squared plus 2x. So if I let my denominator be x squared plus 2x, what's my du? 2x plus 2. Now, at first glance, you look up there and you say, well, that's not up there. That's not in the numerator. However, what if I was to take your du right here? Can you factor something out? You could factor a 2 out, and that would leave me with 2 times x plus 1. And guess what? X plus 1 is up there. Since x plus 1 is up there, now how do we adjust for a constant? Bring out the reciprocal. So you can bring out the reciprocal of 2 and write this as 1/2 times the integral of now 1 over u du. Okay. Since I could factor and x plus 1, exactly x plus 1 was up here, I can rewrite this as 1/2 times the integral of 1 over u du. So this is 1/2 times the natural log of x squared plus 2x plus c. So we do need to know how to divide these expressions. Didn't explain this one in the video, but that's okay. You can look back at that one. Let's do this one here. Why do we want to divide? Because if the power in the numerator and denominator is the same, or the power in the numerator is higher than the denominator, then it's not a natural log integral. And so we need to rewrite this some way algebraically. So now, if you're missing terms, like say that you're dividing by x to the first power, but the highest power in the numerator is x squared, and you don't have an x term, you're going to want to make sure you put plus 0x. So if you're missing terms in what you're dividing by, you'll want to put in zeros. Those have to be there. If you don't put them there, when you start working the problem out, you're going to have things that you can't line up correctly. And we want to line things up correctly because it makes it easier for us. Alright, so what would I have to say times x to give me x squared? X. So I say x times both of these. So x times x is x squared. That should be the same thing right underneath. Now this will be different. X times a positive 1, that's plus x over, or equals. Now remember, whatever you write down here, you always subtract. So I have to subtract this, and I have to subtract this. This term cancels out like it should, and that left me with, I have 0x and negative 1x. So it leaves me with negative 1x. Now, what times x is negative x? Negative 1. Okay? So, negative 1 times x, again, is negative x. It's exactly the same. It should be. Negative 1 times positive 1 is what? Negative 1. Now, I don't have my constant here yet, so what I need to do is bring it down. So I'm going to put a plus 1. Now before you start adding things together and trying to cancel everything out, remember, whatever I have written down here, I have to subtract. So I have to subtract the first term, which will make that a plus, and the second term, will make that a plus. So when you put those two together, those cancel out like they should. The first one should always cancel out. And then I have 1 and 1, that's 2. So how do I write my remainder? Plus 2 over x plus 1. So let me show you now where long division in integrals is handy. Let's say that I had the integral of x squared plus 1 over x plus 1 dx. Notice that the power on the top is the same or higher, which in this case higher than the power on the bottom. So once you do long division, you can rewrite your integrand as now this right here is the same. X minus 1 plus 2 over x plus 1 dx. So now I can integrate each term separately. Alright, I noticed that this first term, the integral of x, is x squared over 2. The integral of negative 1 is just minus x plus the integral of this last term. Now when you see that, you need to think natural log, right? Because if I let u be x plus 1, then du equals 1. So this can be written as 1 over u du. Alright? So that's going to be 2 times the natural log, the absolute value of x plus 1 plus c. And remember, you can always take your answer, take the derivative of that, and it's equal to your integrand. Alright, since we know what we do now about taking the derivative of natural log And we have went over how to integrate some natural log integrals, even if we have to do algebra first and do long division or whatever. Let's think back to when things were so much simpler, when we were just taking the integral of our basic trig functions back in the beginning of the chapter. We said the integral of sine of x is negative cosine of x plus c, and the integral of cosine of x is sine of x plus c. But for some reason or another, back then, way back when, at the very beginning of maybe the previous chapter, we didn't go over the integral of any other trig functions unless they were the derivative of a trig function. Like we went over the integral of secant squared. Well, what about the integral of secant? We've actually worked that. If you remember earlier, I took the derivative of the natural log of secant x plus tangent of x, and I said that was equal to secant. So what that means is if I integrate secant, I get natural log secant x tangent of x. So that's one of those integrals that you need to know you're going to use from now on in your calculus career. Natural log secant of x plus tangent of x plus c. Integral of tangent of x. Well, earlier, when you're going over derivatives of natural logarithms, we went over the derivative of the natural log of cosine of x, and we got negative tangent of x. So that means the integral of negative tangent would be positive natural log cosine. So the integral of positive tangent is equal to negative natural log cosine. Alright, get two more trig functions. The integral of cosecant of x. Now don't get that confused with the integral of cosecant squared. It's actually one of those crazy logarithms. The integral of cosecant is equal to negative natural log absolute value of cosecant x plus cotangent x. Plus c. So how could you ever remember that? Well, if you remember, its cofunction secant is something similar. It's not the same, but it does involve cofunction and another cofunction, so it is kind of related, kind of similar, because they involve the same cofunctions, but not exactly the same. And then the last one, the integral of cotangent of x dx. So I believe we went over that one too. We're doing derivatives. Natural log of the sine of x. So if you have no more calculus, no more math, no more engineering classes in the future, then I'm not saying you don't need to know these. You still need to know them. But if engineering or mathematics is something that you see in your future, then you've got to know these integrals because they're used just like any other integral. These are the common, these are just the common trig integrals. It's just we didn't define them yet because we had not went over natural log. So it would not make sense to define these other four until after we know how to take the derivative of natural log. Okay. So say that I wanted to find the integral of the secant of 4x dx. What's the u? 4x. What's the du? 4. So I need to bring out a 1/4. Then it's natural log of secant 4x plus tangent 4x plus c. So whatever this is has to stay the same in the answer. Your u's have to stay the same. Since it was an integral, the du, you bring out the reciprocal of the constant.